Hi class, this is partitions and the law of total probability. Let's define a partition of a sample space. Basically what it means is to split the sample space into disjoint yet all-encompassing subsets. Here's the definition. The events A1 through AN form a partition of the sample space S if the AIs are all disjoint, the union of the AIs equals the entire sample space S, and the AIs are non-trivial in the sense that the probability of AI is greater than 0 for all I. Remark, when an experiment is performed, exactly one and only one of the AIs occurs. An easy example, A and its complement, A bar, form a partition, whatever A may be. A specific example, vowels and consonants form a partition of the letters, at least if you pretend that A, E, I, O, and U are the only vowels. Let's suppose that A1 through AN form a partition of S and B is some arbitrary event. I'm going to decompose B into pieces involving the partition. In particular, B equals the union from I equals 1 to N of all the intersections of the form AI intersect B. And this is a little tough to look at for the first time, so a picture is worth 1,000 words here. There's the event B in the big red circle, and the partition A1, A2, A3, A4. You can see all the A's are disjoint, and they encompass the entire sample space, the rectangle. So B is composed of pieces of itself intersecting all the AIs. So you have A1 intersect B, A2 intersect B, A3 intersect B, and even A4 intersect B. If you add all those up, you get B. And that's what the expression at the top of the page means. B equals the union from I equals 1 to N of all of the intersections of AI intersect B. So, if A1 through AN is a partition, we can decompose B into pieces of the AIs. And because of that, we can calculate the probability of B in terms of those pieces. The probability of B equals the probability of the union from I equals 1 to N of those intersections, AI intersect B. Those intersections within the union are all disjoint, so the probability of the union is the sum of the probabilities of the intersections. And again, that's since the AIs are disjoint. Now I apply conditional probability, and the probability of the intersection is the probability of AI times the probability of B given AI. And so we keep that sum. This is the law of total probability. And I've got to say, it's not only a great idea, it's the law. Here's an example. This is involving that easy little partition A and A bar. We actually looked at that in the last section. So since A and A bar are partition, then the probability of B equals the probability of A times the probability of B given A plus the probability of A bar times the probability of B given A bar. Very easy. In particular, suppose that we have 10 Georgia Tech students and 20 UGA students, and they're taking a test. The Tech students have a 95% chance of passing the test, but the UGA students, at least assuming they don't cheat, only have a 50% chance of passing. Again, not a surprise. Let's pick a student at random and determine the probability that he or she passes. By the law of total probability, the probability that the random student passes, this is just by the example at the top of the page, equals the probability that you're Georgia Tech times the probability that you pass given Georgia Tech plus the probability that you're UGA times the probability that you pass given that you're UGA. And let's do a plug and chug. Georgia Tech students encompass 1/3 of the population, 10 out of 30, 1/3. The probability that you pass, given that you're Georgia Tech, is 0.95. Then plus probability of UGA, 2/3, times the probability to pass, 50%. And when the smoke clears, the overall probability passing is 0.65. Fantastic. Easy example. And this will pave the way for Bayes' theorem, which we'll be looking at in the last and final lesson. So see you then.